All right, guys, this is the part 2 video for the application problems. So the first thing that I want to draw your attention to is some formulas that go along with some of these applications. And I want to come down here to this doubling time formula because this is not the formula that I use for doubling time. So I'm going to get rid of this formula and I'm going to replace it with two different formulas. And the first one is the one that we use to find the doubling constant, K, which you need for the formula. The second one is the one that you're going to use to actually solve the problem. So to find K, you use the formula 2P equals P e the number to the KT power. P is the population, K is the constant we're looking for, and T is time. Now, once you find K, you can use a second formula to find T. So the second formula, when you're trying to find time, is P of T equals, that means the population after a certain amount of time has gone by, P sub 0, that's the initial population, e to the KT power. And this time you'll know K because you will have just found it. So after you find K, you use it in this formula. So it's similar to the continuously compounding interest formula, except we'll be looking for time. All right, so those two formulas are ones I'm actually going to use, and they are used in some of these applications. So if you look at the applications here, the first application is talking about half-life and carbon decay. So the formula that we are going to use is the carbon-14 decay formula. And I'm going to write it out so you have it because these formulas, you guys can probably see it easier than I can on my screen. But the formula for this one is A of T equals A sub 0 E, and then it's negative, that doesn't look right, hold on, negative 0.3 zeros, 1, 2, 3, 1, 2, 1, T. All right, so let's see here. This is saying we're talking about carbon-14 decay, which we have a specific formula for. So assuming the half-life is going along with this carbon-14 decay, it says how long is it going to take 3 grams to become 1 gram? So 3 grams is the initial amount. That's the A sub 0. 1 gram is the future amount. That's A of T. And we're looking for what T actually is. So we're going to plug these two values in. And it's going to look like 1 equals 3 e to the negative 0.000121 t power. And since e is involved, we're going to use natural log. But before we can use natural log, we have to isolate the exponential part, which means isolate the e. So I'm going to divide both sides by 3 and make this 1/3 equals e to the negative 0.000121 t power. Now I'm not actually going to divide the 1/3 right now. I'm going to do all this stuff in the calculator. But in order to get rid of an e, I'm going to use natural log. So when I use my natural log, I'm going to ln both sides. Again, not actually doing anything at all yet, but the natural log and the e are going to cancel. On this side, I'll have ln of 1/3, whatever that is. Again, it doesn't matter at this point. But on the other side, the natural log and the e cancel, which just leaves me with the power, negative 0.000121 t power. Now, in order to isolate the t, I would divide both sides by that ugly decimal in the front. And when I do that, now here's where I'm going to put it all in the calculator. I'm going to put in natural log 1 divided by 3, close the parenthesis, and then hit divided by that big, long, ugly decimal, and let the calculator do all the heavy lifting. And do we have to round it anywhere specific? It doesn't say. I went to 3 decimal places just to be safe. So when I plugged all this into the calculator, I got approximately 9079.440 for T. So 9,000 years. So there's some carbon decay application. Let's talk about the doubling time and then finding out how long it takes us to get somewhere. So when we're dealing with doubling time, we're going to have to find K when it's not given to us. And when K is not given, we use that first formula I gave you, 2P equals PE to the KT power. Now, after we find our K, we're going to use K. And when we use K, we use it in the other formula. P of T equals P sub 0 E to the KT power, except we'll know K this time. All right, so let's talk about the actual problem now. It says, suppose the population of bacteria in a petri dish has a doubling time of 1.5 hours. So the 1.5 is going to go into this formula for doubling time in the place of T. How long will it take an initial population of 10,000 to reach 100,000? Now, the 100,000 is the future value, which means it will only be involved in the second formula. That's misleading. It makes it look like it goes in for T. The 100,000 is going to go into this formula for future value. The other 2 pieces are going to go into the other formula so that we can find out what the doubling constant is. So we know what P is. It's the initial population. And it tells us right there, the initial population is 10,000. So if I plug it in, I have 2 times 10,000 equals 10,000 E. K is not given. That's the constant we're looking for. But T is 1.5 because it tells us the doubling time is 1.5 hours. So K times 1.5. Now we can simplify this formula a little bit. 2 times 10,000 is 20,000. 10,000 E. And then instead of writing it like this, I'm going to write it as 1.5K just to make it a little bit nicer to look at. Now, once it's in this form, we basically have to do the same thing that we did the last time, isolate the E and use natural log. So I'm going to isolate my E by dividing 10,000 over. And when I divide 10,000 over, I should get 2 equals E to the 1.5K power. Now at this point, let's bring in the ln so we can cancel the E out. And that means 1.5K is all that's left over there. The last thing I do is put all this stuff in the calculator, divide by 1.5. And again, I'm going to put this in and let the calculator do it. Natural log 2, close the parenthesis, divided by 1.5. I rounded to 4 decimal places this time just to be kind of, as detailed as I could without going too crazy. But I got a constant of 0.4621. The more decimal places you use, the more accurate you'll be. Now, this formula doesn't answer the question. This formula gives us the constant that we need to use in the other formula. The other formula is what's actually going to answer my question, because it's asking me how long it takes for the population to grow to a certain amount. It doesn't ask anything about how long it takes to double. So now I'm going to use the future value and use my K. So the future value 100,000 equals initial value we already knew. The initial population was 10,000. E. This time we plug in K, 0.46, whoops, backwards, 4621 T. T is what we're looking for, time. Now, it's still solved in a similar fashion. You have to isolate the E. So we are going to divide both sides of this by 10,000. And when I divide 100,000 by 10,000, I get 10. E to the 0.4621 T power. Again, I have to natural log because I'm dealing with E. We'll cancel. ln 10 equals 0.4621 T. And then just like before, I would divide both sides of this by that decimal. Divided by 0.4621. And let the calculator do it for me. As long as I close the parentheses around the 10, we're going to be in good shape. I only went to 2 decimal places here. Approximately 4.98 equals T. So about 5 hours. Just under 5 hours. All right, the last one is compound interest, and it is not continuously compounded. It's just regular compound interest. And the formula for that is A equals P times 1 plus R over N raised to the N T power. Now let's analyze our problem. We've got Wayne has $12,500 in a high interest savings account at 3.66%. 12,500 is the P, that's the amount invested. 3.66 is the R, but we can't use the percentage. We have to change it to a decimal, 0.0366. You move your decimal 2 places to the left. Then it says compounded monthly. That's important because that's the N value. When it's monthly, N is 12. And we want to know how long is it going to take for it to reach 15,000. So 15,000 is the A value. That's the amount after a period of time has gone by. We are looking for T because the question is how long. So we have every value needed except for the T, which is good. So let's plug in 15,000 equals P, which is 12,500 times 1 plus R is 0.0366 divided by 12 for N, and it's raised to the N times T power. Now, I would probably divide over this 12,500 just to get rid of it. Divide this over 15,000 divided by 12,500 is 1.2. I also probably want to figure out what this number is here so that I can use it in my formula. This one's gone. We moved it over. So 1 plus 0.0366 divided by 12. Oh, God. It's 1.00305. And that's raised to the 12t power. Now, what stinks about it is that when you're doing these problems, you're not supposed to round until the end when possible. And even though that decimal is long, it's not a non-terminating decimal, so you have to use all of it. We won't round until the end. Now, this time, we're not dealing with E. We're dealing with just numbers. So when we're dealing with just numbers, we're going to use log. Log both sides. I'm not actually going to log anything yet. This is log 1.2 equals. Let's drop this power to the front, which is the whole goal of using the log. Log 1.00305. Now I'm trying to isolate the t. The first thing that I'm going to do, because I don't like to put anything in my calculator yet, I'm going to divide out this log on both sides. That leaves me with 12t equals this ugly thing right here. Then I can divide that 12 out as well. And I can do the whole thing in the calculator at one time. Hit log 1.2 divided by log this equals. It'll put something on the screen. The thing it puts on the screen is like 59.8 something. It keeps going. Equals 12t. Leave it in the calculator, that whole long thing, and hit divided by 12 again. When you divide by 12, oh my God, we get 4.989. Which is almost the same answer as the last one. But again, about 5 years. So once you have your final answer, round it to whatever decimal place they tell you to. So whichever one they want you to go to, just go there. But there are just some examples of some word problems to kind of go along with some of this log and natural log application stuff so that you know how these logs and natural logs can be incorporated into real world examples. And this is the end of the last section. So that means the only thing left is the final exam. I hope that you guys have registered for your final already and that you are preparing for it currently so that you are ready to go. I will not be here at this point in the semester, so I wish you all the best. And if you have any questions about anything specifically involving content or grades or anything like that, please contact the department head. Her name is Becky Pearson. Her contact information is in the syllabus directly under mine. So just make sure you check that out in case you need it. Also, please make sure to take advantage of tutoring times before the final exam, because remember, the final exam is going to replace your lowest test score as long as it's higher. And so it can be very helpful in certain scenarios for certain people, and you want to make sure you take full advantage. So again, best of luck, and I will talk to you guys later.